Alright, let's do some introductory wave example problems. A wave on a string is described by this equation, where A is 1 centimeter, B is 4 inverse centimeters, and C is 1.2 inverse seconds. I'm realizing now that I chose a bad variable for C. That is not the speed of light, that's just some parameter. Okay, what speed does the wave travel? What direction does it travel? Alright, first of all, the direction. How do I figure out the direction that the wave travels? Well, it all has a plus sign, right? So the point is, at time t equals 0, this wave just looks like a over bx cubed, right? And it looks like at x equals 0, it jumps up to infinity, right? This is a really bizarre wave. Okay, but now what happens as time increases? I want to find this point that goes to infinity, right? And see how, you know, this big peak in my wave, I guess it's going to do like some weird thing where it goes infinity here and down from infinity there. Anyway, the point, my wave is really weird, that's not the point, but the point is I want to see how fast this point, some particular point in my wave, is moving. As time increases, what have I got to do to x to keep this argument the same? Well, if time goes up, since I'm adding them together, x has to go down. So this wave is going to travel in the negative x direction. Alright? As time goes up, I have to decrease x, I have to make x go more negative in order to keep this argument constant, right? So to follow a particular point on my wave. Alright, now how fast does it go? Alright, well, I can take this equation, let's rewrite it. So I've got a, let's factor out the b in front here. So this is going to be like b cubed times x plus, so I pulled a b out, so I have to divide, b cubed out, so I have to divide both terms here by b. So this is going to be x plus c over b t. And I'm like, oh, okay. So how fast do I have to change x with time? Well, if time goes up by 1 second, x has to go up by, or down by, c over b. So the velocity is just sitting right there. Once I solve it in this form, it looks like x plus vt. And then I know the velocity is just c over b. Alright? So there we go. Alright, fairly simple problem. Before we plug this into our calculator, we look at it and we say, does it have the right units? So C is inverse seconds and B is inverse centimeters. So this is like centimeters per second, or, you know, converted to SI units, meters per second. It's got the right units. Anyway. Next problem. A wave on a string is described by the equation y equals a sine bx minus ct, where a, b, and c are these numbers. Alright, so this is different from the previous wave. Unlike this weird thing that went to plus and minus infinity, this is one of our favorite kinds of waves. This is a sine wave, alright? If this were cosine right here, it would still be a sine wave, right? Because cosines are just sine waves that are shifted by 90 degrees. If it was sine of all of this stuff plus some phase, it would still be a sine wave, alright? And those kind of waves we love. They're very useful, they're very fundamental. So let's dive into this, alright? Now it turns out pretty much everything I'm going to come up with is going to be the same as if this were a cosine or a sine wave with a shift, or a cosine, you know, bx plus or minus ct plus a phase shift. Throwing in the phase shift is not going to change any of the stuff we're going to calculate here. Changing it from a sine to a cosine is not going to change anything, just so you're aware, alright, that what we're doing is fairly universal. The first thing we want to know is what speed does the wave travel and what direction does it travel? Once again, it has to do with the sign right here. As time goes up, if I want to follow a point on the wave, right, if I want to follow a maximum of my sine wave or a minimum of my sine wave, that's a point, right? If I wanted to follow the minimum at 0 when time is equal to 0 and see how it moves with time, I want to keep this argument 0. As time goes up, what have I got to do to x to keep this argument 0 or keep it at some fixed value? As time increases, x has to increase. So I know that it's going to travel in the plus x direction. What is the velocity? Once again, I just have to factor this, alright, so that I have x plus something, right? So this is going to be sine of, and let's factor out the b, and then I have like bx minus c over b t, alright? So it's going to travel in the plus x direction with a velocity of c over b. There it is, x plus v, or minus vt, right? So there's our velocity right there. Okay, so a sine bx minus ct. The next thing it asks for is what is the wavelength, what is the amplitude of the wave? The amplitude is just right there, right? That is the amplitude of the wave. Now don't get confused, my sine wave goes like this, right? the amplitude is that distance right there. The peak to peak distance, right, from the highest it goes to the smallest it goes to the highest it goes, that is 2 times the amplitude. But the amplitude is just how far it goes away from 0. So the amplitude is just A. That's what the amplitude is. All right, now we want to know the wavelength and the period. All right, so our wave, excuse me, once again it was A times Bx, is A times sine of Bx minus Ct, right? Did I get that right? Okay, and we want to know so we got the amplitude, wavelength, period, frequency. So we know wavelength, period, frequency, and then we want to know angular frequency and wave number. So angular frequency and wave number. All right, well, what is the wavelength? All right, well, let's look at this, right? If I've got a wave, okay, basically the wavelength is how far I have to go before this wave repeats itself, right? So, so wavelength is I freeze my wave in time, right? So I'm not letting it propagate in time, and I say, you know, I've got this wave, let's say I start at the origin, how far do I have to go before my wave starts to repeat again, all right? So at time equals 0, if I look at time equals 0, x comma time equals 0, this is A sine of Bx, right? Now at x equals 0, this is just A sine of 0, right? Now I'm going to follow with time frozen. I'm going to increase x until I get to where the wave starts again. Where the wave starts to repeat itself is when I have moved the argument of my sine by 2 pi, right? So if I go 1 wavelength away, all right, that's when I get A sine of 2 pi, right? So if I plug in 1 wavelength for x, that's what makes my argument equal 2 pi, all right? So that means that B times 1 wavelength, that's the argument when x is 1 wavelength, is equal to 2 pi. And I go, oh, the wavelength is just 2 pi over B. There you go. I've got the wavelength, all right? What's the period? So for the period, again, we're going to plot our wave, but only instead of holding time constant, we're going to hold x constant. So if x is equal to 0, when we plot our wave as a function of time, right, it's going to go like this, right, as a function of time. And I want to know how long do I have to wait if I keep x constant, right, and this wave is traveling through and I watch at some point, how long do I have to wait for the wave to repeat itself? All right, well, at x equals 0, t equals 0, my wave is just A sine of 0, right? But if I keep x constant but increase time to 1 period, right, that's when the argument of my wave has changed by 2 pi, all right? And so I look at this and I say y at x equals 0 and time t, right, time 1 period, is, right, the argument is 2 pi. So if I look at my wave at x equals 0 and at 1 period, I'm going to have A sine minus c times 1 period is equal to A sine 2 pi. Okay, I've got this minus sign, and that just means that my wave is traveling one way or the other, right? So I'm going to ignore the minus sign right here and say, well, let's just say because of the minus sign, because the wave's traveling the other way, I'm going to wait for the phase to change by negative 2 pi, all right? And then we just say c times the period is equal to 2 pi, and then my period is just 2 pi over c. Once again, c was a really bad choice, because when we do like optics, the velocity of the wave will be c, but that's not the velocity of the wave, that's just some parameter. I should have thought about that before I wrote it down. But anyway, my period is just 2 pi over this thing right here, right? It's just how far it has to go. All right, there's my period. Okay, what's the frequency of the wave? The frequency is just equal to, what is the frequency equal to? It's just 1 over the period, right? So that's just going to be c over 2 pi, where c is not the speed of light. All right, what is omega? Omega is the angular frequency. So the frequency is the number of cycles we go through each second. So it's just 1 over the period. If the period is half a second, we go through 2 cycles each second, right? Each period is a half, so we do 2 of them in 1 second. Angular frequency is the number of radians we go through per second. All right, so we do 1 cycle. If we did 1 cycle per second, that's 2 pi radians per second. Or in other words, whatever the frequency is, number of cycles per second, I just have to multiply by 2 pi to get the number of radians per second. All right? So this is the number of radians of phase that our wave goes through every second. Wave number is like the same thing as angular frequency, but with space. It's like a spatial angular frequency. It's if I freeze my wave in time and move in x, how many radians of phase do I go through for each meter that I travel along the wave? All right, and so k is just equal to 2 pi over lambda, right? Just like, so you could write the angular frequency as 2 pi over the period in time. Lambda is kind of like the period in space, right? Instead of freezing my position and watching how long it takes to repeat, I freeze my time and I walk in space and see how far I have to go for it to repeat. So lambda is like a spatial period in a sense, and so my wave number is just 2 pi over lambda, and I've already found lambda, so this is just k is just 2 pi over lambda, so that's just going to be b. All right, b is just my wave number. All right, okay. And it turns out if I plug my period in, let's not forget this. Let's plug my period in here, right? If I plug in 2 pi over c into here, I just get c. And I find, oh, look at this. Omega is just c, and k is just b. And that's really cool because oftentimes kind of a standard way to write a sine wave is kx minus omega t. All right, and that's what we found is, oh, b is just k, right? And c is just omega. All right. So I think we found everything we needed to for this problem. Let's do one more problem quickly. I have a 2.5 meter long string that weighs 10 grams. So I know the length of the string, I'll call it L sub s. I'm given the weight of the string, that's really a mass, right, because it's in grams. I did the standard American colloquial ways when I really meant it had a mass, all right? I fix one end of the string to the wall. I tie a 1 kilogram weight on the other and then hang the string over a pulley 2 meters from the wall. So the part of my string between the wall and the pulley, I'll call that L, and that's 2 meters. So I'm given that, right? 2 meters. All right? Okay, and I have a 1 kilogram weight. All right? So I have a weight, all right? My weight has a mass of 1 kilogram, and I hang it over the pulley 2 meters from the wall. I then flick the string near where it is attached to the wall, and I measure how long it takes for the disturbance to travel from the wall to the pulley, reflect back, and return to the wall. How long will it take? Okay, so I'm going to flick the string, all right, and basically it's going to go down the string to the pulley, reflect off of where the string hits the pulley, and back. So the distance it's going to travel is 2L. And I want to know the time, I'll call that tau, that it takes to do that. Well, the time is just going to be the distance, 2L, divided by the velocity that the wave travels, all right? What is the velocity of the wave? Well, we know the velocity of waves on a string is just the square root of the tension divided by the linear mass density, all right? So here's our equation. The time is just 2L divided by the speed of the wave, but the speed of the wave is the square root of the tension over the linear mass density. All right, so how do I find the tension? The tension is just equal to, right, the force on the string, right? We put the string over, it's tied to the wall, and then it goes over a pulley, and then we have this mass, all right, of the weight, mass of the weight, all right? And the tension is just going to be the force that it pulls down with. So that's going to be the mass of our weight times g, all right? We're given the mass of our weight. That's another thing we're given. We'll call it m sub w, and that was, we said 1 kilogram, right? 1 kilogram. So that's a given. We've got that. That's the tension. What's the linear mass density? The linear mass density is the mass per unit length of our string. We're given the mass of our string. I called that m. Maybe we should call it m sub s, just to be clear, all right? M sub s is 10 grams. So m sub s is equal to 0.01 kilograms. All right, we've got m sub s. And then that's the mass of the string, and we divide by the total length of the string. We call that ls, right, the 2.5 meters. So we have the tension. We have the linear mass density, so the velocity is just going to be the square root of the tension, mass of the weight times g, divided by mass of the string, divided by the length of the string. We've got the velocity, and then I just find tau by, I'm given 2L, I divide by the velocity, all right? I plug that velocity in, and I've got it. So there it is. All right, now, Maybe I always say do things algebraically before you plug things in, but this is looking maybe messy. Maybe we're going to calculate the velocity and just keep all of the digits and then plug it in. All right, but we can still test units, right? Because I look at this and I say meters divided by meters per second, that's going to give me seconds, right? So I have the right units. If L increases, it takes longer. If the velocity increases, it takes less time. That makes sense. Let's look at our velocity. All right, our velocity, these masses cancel out, and I have G, so I have units. I have kilograms, meters per second squared, times meters over kilograms. All right, and I take the square root of that. The kilograms go away. I've got meters squared per second squared, square root. All right, my velocity has the right units. Let's see if the velocity makes sense. All right, if my weight is bigger, that's going to be more tension in the string, and you'd expect a stronger restoring force. That ought to make it go faster, right? If my string has more mass for my string means more inertia. It's going to make it slower, all right? How would a longer string affect my velocity? Well, if I have the same mass on my string but I make it longer, that means that I've taken that mass and I've spread it over a longer string, so any little piece of the string is going to have less inertia. It ought to make the waves go faster. So a longer string ought to make it go faster. Bigger gravity, that means gravity's pulling down on this weight more, there's more tension in the string, a stronger restoring force, I would expect it to go faster, all right? So I'm looking at things, they seem to make sense. In the limit as the mass of my string goes to 0, the velocity goes to infinity. In the limit as the mass of my weight goes to 0, my velocity goes to 0. So it all sort of seems to make sense. It has the right units, it scales the right way, it does what I think it should do in certain limits. So I feel fairly confident that if I plug my numbers in carefully, I will get the right answer.